Hello everybody. In this video we're going to be covering section 14.4, the hydrolysis of salts. We're going to learn to predict whether a salt solution will be acidic, basic, or neutral. We're going to calculate the concentrations of various species in a salt solution, and we're going to describe the acid ionization of hydrated metal ions. So up until now we've talked about ionic compounds, we've talked about salts, and we know that when we put them in water, they're going to dissociate out into cations and anions. What we haven't considered now is that those cation and anions are actually able to have further chemical reactions with water and behave as both acids and bases. This can play out in a number of ways, where this aqueous salt solution could be acidic, it could be basic, or it could be neutral, and this is going to depend on the relative strength of the acids and bases of the salt's constituent ions. The best way to look at this is with some examples. So we have ammonium chloride that dissociates out into ammonium ions and chloride ions. What we need to do is to think about what the conjugate acid base is of these. Okay, so this guy could have accepted a proton, so it could be ammonia, a weak base, accepting a proton, and it would have produced this ion. All right, we can go and look up the Kb value for ammonia, and we can see that it is measurable and has some value because it's a weak base. And that means that the Ka of this, its conjugate acid, is going to be some value greater than 0, right? We could have also just looked up the Ka value of the ammonium ion directly, but this is a little bit more general of a methodology for this. That means that the ammonium ion is a weak acid, and it's going to have an acid reaction with water where it produces hydronium ions. HCl is a strong acid, right? So if we imagine that this would be the conjugate base of HCl, right? If I added an H there, Ka is immeasurably large, which means that the Kb is very, very small because it has that inverse relationship. That means that chloride ions don't undergo appreciable hydrolysis. This reaction is not going to happen to any appreciable extent. In this situation, we have a sodium ion, and we're going to see that sodium ions do not participate in hydrolysis. And we have the acetate ion. The acetate ion is the conjugate base of acetic acid. Acetic acid is a weak acid, and its Ka is measurable, meaning that its Kb is greater than 0. So the acetate ion is a weak base, and this reaction will happen to some extent in water. At this point, we can see a bit of a pattern here. When we have a weak acid, the conjugate acid of a weak base, all right, we're going to see a reaction happen, all right. But when we have the conjugate acid or base of a strong acid or base, we are not going to see anything happen, okay. So the stronger the acid or base that this is representing the conjugate acid or base of, the less likely anything is going to happen because they have that inverse relationship. We could get into a situation where we have something that is amphoteric. For instance, sodium bicarbonate. We put that into water, and we get this bicarbonate ion. We've already seen that the bicarbonate ion is amphoteric. It can act as both an acid or a base, but we want to know which of these is going to happen. What we need to do is to go look at these Kb values and these Ka values. We can see that Kb is quite a bit higher than Ka. Therefore, in solution, it's typically going to act as a base, and the solution will be basic. So aside from group 1 and group 2 metals, all right, which includes the sodium that we discounted before, all right, most metal ions will undergo acid ionization to some extent when dissolved in water. So the big takeaway when we have group 1 and group 2 metals, we're not seeing any hydrolysis. When we don't have that, we're going to have to start to consider hydrolysis. The acid strength of these complex ions typically increases with increasing charge and decreasing size of the metal ions. Okay, so when we have a small ion with a lot of charge, we're concentrating that charge down. We see high acid ability, like the example here where we have zinc with this 2 plus charge. We got a small ion with the 2 plus charge. Where we have a larger ion here with the copper, we're seeing that it has a relatively low pKa. And then if we increase the charge but keep it roughly the same size as the zinc, we are going to see some intermediate amount here of pKa. So we have talked a lot about the ions of the metals being stabilized by by water molecules, but sometimes what winds up happening is they actually form a true covalent bond with the metal to form a complex ion. This is the example with aluminum. If I take aluminum nitrate and I add water to it, I'm actually going to form this aluminum complex here, where I have water molecules covalently bonded to the aluminum. Now, you should be able to recognize at this point that we are now setting up a situation that looks like one of those ternary acids, where I have a central atom bound to oxygen, bound to hydrogens. What's going to wind up happening is that these metal hydrates can release protons in a stepwise fashion. This is what we call a polyprotic acid, and we're going to talk a little bit more about that in the next chapter. So as we start with this aluminum complex, it can give up a proton and produce this guy here, where we have one of the waters bound to it with one less proton, and it can continue to do that over and over again, donating protons from those different water molecules.